Section: Introduction. In this section, we introduce large language models, LLMs, which are built to understand and create text, allowing them to perform various tasks like translation, summarization, and answering questions. By incorporating visual data, large multimodal models, LLMs, enhance these capabilities, enabling more complex tasks such as image captioning and video analysis. For LLMs to effectively tackle these tasks, visual reasoning is crucial, as it helps them process and connect different types of information logically. To enhance the problem-solving skills of LLMs, we advocate for a step-by-step reasoning approach that breaks down complex tasks into simpler parts. This method mirrors human thinking, allowing models to follow their reasoning processes and maintain logical consistency. Previous studies have shown that prompting or fine-tuning LLMs to produce step-by-step rationales can improve their reasoning abilities. However, many existing studies struggle with step-by-step multimodal reasoning tasks, and current visual reasoning benchmarks often overlook the importance of intermediate reasoning steps, focusing mainly on final task accuracy. To address these gaps, we propose a comprehensive evaluation framework for step-by-step visual reasoning, introducing the Visual Reasoning Chain, VRC bench. This benchmark covers 8 categories, including visual reasoning, math and logic reasoning, and medical imaging, featuring over 1,000 challenging samples and more than 4,000 verified reasoning steps. We also present a new metric that assesses the quality of visual reasoning at the individual step level, emphasizing both correctness and logical coherence. Additionally, we explore the benefits of combining beam search with multi-step curriculum learning in training visual reasoning models. This approach allows models to gradually develop skills, starting with simpler tasks and progressing to more complex reasoning scenarios, enhancing both performance and interpretability. Our experiments show that our model, LlamaV-o1, outperforms existing methods, including the LlamaV-o1 model, across various evaluation metrics. In summary, we present a unified framework aimed at advancing step-by-step visual reasoning through a new benchmark, a novel evaluation metric, and a model trained with curriculum learning. Our contributions include the first benchmark for multimodal multi-step reasoning tasks, a metric for assessing individual reasoning steps, and a method that combines curriculum learning with beam search for effective visual reasoning. Section Summary. In this section, we introduce a comprehensive framework to enhance step-by-step visual reasoning capabilities in large multimodal models, LLMs, through the development of the Visual Reasoning Chain, VRC benchmark, which evaluates multi-step reasoning across diverse categories. We also propose a novel evaluation metric that focuses on the quality of individual reasoning steps and present our model, LlamaV-o1, which combines multi-step curriculum learning with beam search to improve reasoning efficiency and accuracy. Section: Step-by-Step Visual Reasoning Benchmark, VRC bench. In this section, we introduce a step-by-step visual reasoning benchmark called VRC bench to thoroughly evaluate reasoning abilities in complex situations. This benchmark is designed to assess both the logical flow of reasoning and the accuracy of the outcomes produced by language models. By incorporating a variety of datasets covering topics like science, mathematics, medical knowledge, social sciences, and data interpretation, we ensure our evaluation captures a wide range of reasoning aspects. To create this benchmark, we include samples from several specific datasets across different domains. We provide examples of the questions and answers in our benchmark, along with data distribution visuals. By integrating these diverse sources, we can evaluate the model's abilities to handle complex inquiries effectively. We generate step-by-step reasoning using a semi-automated annotation process that includes detailed rationales. In the category of mathematical and logical reasoning, we use datasets like MathVista for various math problems and DynaMath for dynamic challenges. ChartQA helps us evaluate visual reasoning through chart comprehension. For scientific reasoning, we include samples from ScienceQA and MMMU Medical, which focus on scientific knowledge and medical imaging tasks, respectively. To assess cultural and social understanding, we use samples from OMBench, which evaluates social context comprehension. We also include datasets like Logic Vista and Blink IQ for complex visual perception and Doc-VQA for document understanding. We adopt a semi-automatic method to generate step-by-step reasoning responses, starting with the GPT-4o model to create detailed reasoning steps and answers. We carefully craft prompts to guide the model in producing logical reasoning. This approach allows us to generate consistent reasoning chains that include all necessary steps to reach the answers. To ensure accuracy, we perform manual verification of the generated reasoning steps. A team of verifiers reviews the reasoning chains and final answers, making adjustments for clarity and correctness. Our benchmark includes examples from over 8 diverse categories, and we ask verifiers to add missing steps when needed. We discard examples with fewer than 3 reasoning steps, except for some from Math Vista, which can be addressed in 2 steps. More than 25% of the data was corrected during verification, resulting in over 1,000 samples and 4,173 verified reasoning steps. This manual verification is crucial for establishing a reliable ground truth for evaluating language models. Regarding our evaluation framework, we highlight the limitations of previous methods that do not rely on a set ground truth. While these methods allow flexibility, they can lead to inaccuracies in assessing reasoning quality. We emphasize the importance of having a ground truth for scoring, which helps us identify and address inaccuracies effectively. To improve evaluation accuracy, we use GPT-4o to compare model predictions against a reliable reference. This approach allows us to evaluate reasoning quality using specific metrics that focus on alignment and accuracy. Our metric is based on the reference-free Roscoe suite and includes measures like faithfulness step and faithfulness token to assess alignment and informativeness. We also consider attributes like hallucination and redundancy to identify irrelevant or repetitive reasoning. The final scoring averages all attribute scores for a comprehensive evaluation of reasoning quality. Additional details about the scoring process are provided in the appendix. Section Summary. In this section, we introduce the VRC bench, a step-by-step visual reasoning benchmark designed to evaluate the logical progression and accuracy of reasoning in complex scenarios across diverse domains. We detail our semi-automated annotation process for generating reasoning steps, emphasize the importance of manual verification for establishing a reliable ground truth, and outline our evaluation framework that utilizes a reference-based metric to enhance the accuracy of reasoning assessments. Section. Proposed Step-by-Step Visual Reasoning Model, LlamaV-o1. In this section, we propose a step-by-step visual reasoning model called LlamaV-o1, which aims to enhance multimodal reasoning in large multimodal models, LLMs. Our approach includes several important contributions. First, we utilize curriculum learning to train the model in a progressive manner, beginning with basic tasks like summarizing approaches and generating captions from questions, before moving on to more complex, multi-step reasoning. This structured training helps the model handle complexity better, improves logical coherence, and allows for effective generalization in challenging situations. Second, we implement an efficient beam search technique for inference, which generates multiple options simultaneously and selects the best one. This method not only ensures high-quality outputs but also significantly cuts down on computational costs, achieving consistent scaling compared to traditional methods. We recognize that LLMs are powerful for understanding and generating content across various data types, but they face challenges in complex reasoning scenarios. Models often struggle with step-by-step reasoning, which requires maintaining consistency and clarity across multiple steps. Curriculum learning, inspired by human education, addresses this by training models progressively, starting with simpler tasks and gradually introducing more complex ones. This method has proven effective in improving performance in multimodal tasks like visual question answering and captioning. By adopting a progressive training strategy, we help models build foundational skills incrementally. For multimodal models, this structured approach allows them to first learn basic relationships between different data types, such as text and images, before tackling more complex scenarios. This strong foundation enhances logical reasoning and coherence in multi-step tasks, enabling models to maintain consistency across steps. Additionally, curriculum learning helps prevent issues like catastrophic forgetting, which can occur when models are trained directly on complex tasks. We also emphasize the importance of multi-step chain-of-thought reasoning for complex tasks that require sequential decision-making. This approach allows models to break down problems into smaller, manageable parts, ensuring transparency and consistency. For example, answering a complex question about an image involves identifying objects, understanding their relationships, and synthesizing this information into a coherent answer. By embracing multi-step reasoning, we align models closer to human-like problem-solving, paving the way for more robust AI systems. Our multi-step reasoning process includes several stages. First, we ensure task understanding by grasping the question and context. Next, we summarize the visual data to gain a holistic view, which helps focus on relevant actions. Then, we generate detailed captions to accurately interpret visual elements. Following this, we engage in logical reasoning to locate and interpret the necessary data, breaking the task into sub-goals. Finally, we produce the final answer based on our reasoning and the extracted context. This structured approach reduces errors and enhances interpretability, reinforcing our model's ability to handle each stage effectively and improving their performance on tasks requiring logical reasoning. Section Summary. In this section, we propose a step-by-step visual reasoning model, LlamaV-o1, which utilizes curriculum learning to progressively train large multimodal models, LLMs, for improved logical coherence and generalization in complex tasks. We also implement an efficient beam search technique to enhance inference, allowing for reduced computational costs while maintaining high-quality outputs through structured multi-step reasoning. Section: Data Preparation and Model Training. In this section, we outline our approach to implementing a curriculum learning strategy for model training, which we divide into 2 stages. Each stage is designed to gradually improve the model's reasoning abilities while ensuring it understands multimodal inputs. In Stage 1, we focus on training the model to generate 2 key outputs: a summary of the approach needed to answer a question and a detailed caption that describes important aspects of the input data, like visual elements in an image. We use training data from 18,000 samples in the CAP-QA split of the PIX-MO dataset and 57,000 samples from the GO170K dataset. The CAP-QA dataset provides examples with grounded captions based on questions, while the GO170K dataset includes question-answer pairs with reasoning steps. This stage helps the model learn to contextualize inputs and outline a high-level reasoning plan, enabling it to break down problems into simpler parts. In Stage 2, we build on the foundation established in Stage 1. The model is trained to not only generate summaries and captions but also to provide detailed reasoning and derive the final answer. We utilize the original LlamaV-o1 dataset, which contains 99,000 structured samples from various domains, including general VQA and science-targeted VQA. Each sample includes a summary, caption, detailed reasoning, and the final answer. The training in this stage involves multi-step interactions, allowing the model to refine its logical flow and integrate information from summaries and captions into actionable reasoning steps. The multi-step training methodology is crucial for the model's success. By the end of Stage 1, the model has learned to organize its thoughts and outline a strategy, which prepares it for the detailed reasoning required in Stage 2. This structured approach enhances the model's interpretability, accuracy, and robustness, enabling it to excel in complex multimodal reasoning tasks. Our results show that by using datasets like PIX-MO and LlamaV-o1 within a curriculum learning framework, the model effectively transitions from high-level understanding to detailed reasoning, achieving state-of-the-art performance in multi-step reasoning benchmarks. For model training, we leverage the PIX-MO and LLamaV-o1 100K datasets, employing a curriculum learning strategy alongside a supervised fine-tuning (SFT) approach. We select LLAMA 3.2 to 11B Vision Instruct as our base model due to its strong multimodal reasoning and instruction following capabilities. The fine-tuning process involves optimizing all parameters, allowing the model to adapt to the structured reasoning tasks from the datasets. We conduct training on a high-performance computing node with 8 NVIDIA A100 GPUs to efficiently manage the large-scale dataset and computational demands. During the initial curriculum learning stage, we fine-tune the model on the PIX-MO dataset to develop foundational reasoning skills, such as generating summaries and captions. Additional training details, including epochs, learning rate, optimizer settings, and batch size, are provided in the appendix for reproducibility. To optimize inference efficiency, we adopt a beam search strategy that enhances both efficiency and reasoning quality compared to existing methods like LlamaV-o1. Our approach balances computational complexity with output quality, allowing for faster and more reliable inference. Unlike LlamaV-o1, our method does not require a rigid output format, simplifying the reasoning process and enabling the model to focus on generating high-quality outputs across various reasoning scenarios. The beam search technique allows us to generate multiple reasoning paths in parallel and select the best one, improving the quality and consistency of the model's outputs. Our method's computational efficiency is notable, with an inference time complexity of linear scaling, which is significantly more efficient than LlamaV-o1's quadratic scaling. This ensures our approach can handle larger datasets and more complex reasoning tasks without a proportional increase in computational costs. Section Summary. In this section, we outline our curriculum learning strategy for model training, which consists of 2 stages. The first focuses on developing foundational reasoning skills through summarization and caption generation using datasets like PIX-MO, while the second stage enhances detailed reasoning and answer generation using the LLAVA COT dataset. We also implement a beam search strategy to improve inference efficiency and output quality, allowing our model to handle complex reasoning tasks more effectively. Section: Experiments. In this section, we evaluate the performance of our proposed model, which we trained using a curriculum learning strategy. We use LLAMA 3.2 to 11B Vision Instruct as our baseline model, benefiting from its strong vision language understanding. Our training involves the PIX-MO subset and LLAVA COT 100K datasets, which are specifically chosen to support tasks that require step-by-step reasoning. The curriculum learning framework allows our model to start with simpler tasks, like generating summaries and captions, and gradually move to more complex multi-step reasoning tasks that require detailed logic and final answers. To measure the effectiveness of our approach, we assess the model using our new reasoning benchmark, which tests multi-step chain of thought abilities in multimodal contexts. We also compare our model against 6 widely used multimodal benchmarks from LLAVA COT, covering areas such as visual reasoning, math problem solving, and scientific reasoning. This thorough evaluation shows that our method is robust, with notable improvements in reasoning quality and efficiency compared to the baseline. For our experiments, we fine-tune LLAMA 3.2 to 11B Vision Instruct using the Llama Recipes framework in a supervised manner. This strong foundation allows us to implement our curriculum learning strategy effectively, training the model on progressively more complex reasoning tasks. The training datasets, PIX-MO and LLAVA COT 100K, are tailored for multi-step reasoning and detailed explanations. For evaluation, we use a variety of benchmarks, including our proposed reasoning benchmark and 6 established ones: MM-STAR, MM-Bench, MM-VET, Math-Vista, AI2D, and Hillusion. These benchmarks assess the model's capabilities in visual question answering, mathematical and scientific reasoning, and dealing with language and visual errors. Our proposed benchmark focuses on step-by-step reasoning and final answers, with evaluations conducted using a fuzzy strategy where GPT-4o serves as the judge, ensuring thorough assessments of the outputs. To ensure consistency, we use the VLM Eval Kit framework, as done in LLAVA COT, for evaluating all models across the 6 established benchmarks. This open-source toolkit promotes reproducibility and allows for direct performance comparisons. Our results show that our model significantly outperforms existing methods on our reasoning benchmark. We compare final answer accuracy and step-by-step reasoning performance against state-of-the-art models. While models like GPT-4o, CLAUDE 3.5 Sonnet, and Gemini 2.0 Flash show strong reasoning skills, our approach achieves better final answer accuracy and competitive step scores. This demonstrates our model's ability to produce accurate outputs while maintaining logical coherence in multi-step tasks. We also present a category-wise performance comparison, where our model excels in challenging areas like chart and diagram understanding, scientific reasoning, and OCR and document understanding. These improvements highlight our model's capability to tackle tasks that require both visual and logical reasoning effectively. In summary, our method achieves the highest average score among open-source models on 6 established benchmarks, surpassing others like LLamaV-o1. Our model shows particular strength in reasoning-intensive benchmarks, validating its effectiveness in handling diverse multimodal tasks. By utilizing curriculum learning and optimizing inference efficiency, we balance reasoning accuracy with computational complexity. Our performance improvements are complemented by a strong ability to manage logical errors and visual illusions, as shown in benchmarks like HallusionBench. We also provide a qualitative comparison, demonstrating that our model outperforms recent models in both reasoning steps and final answers. Section Summary. In this section, we evaluate our model trained with a curriculum learning strategy based on LLama 3.2 to 11b Vision Instruct, demonstrating significant improvements in reasoning quality and efficiency across various multimodal benchmarks. Our approach excels in multi-step reasoning tasks, achieving the highest average scores among open-source models and outperforming existing methods in several challenging categories, highlighting its robustness in handling complex visual and logical reasoning tasks. Section: Ablations. In this section, we examine the effects of our proposed components of LlamaV-o1 on enhancing performance in complex visual reasoning tasks across 6 multimodal benchmarks: MM-Star, MM-Bench, MM-Vet, MathVista, AI2D, and Hallusion. By implementing a curriculum learning strategy alongside multi-step chain of thought reasoning, we achieve an average score of 66.08%, showcasing our model's capability in reasoning-intensive tasks. When we add beam search to optimize reasoning path selection, our performance improves further, reaching the highest average score of 67.33%. Notably, we see significant gains in benchmarks like MM-Vet, where we score 65.40% compared to 61.88%, MM-Star with 59.53% versus 58.13%, and AI2D at 81.24% against 80.18%. These results emphasize the effectiveness of our combined approach of progressive training and optimized inference, allowing our model to generalize better and consistently provide accurate reasoning. This reinforces the value of our contributions to advancing multimodal reasoning systems. Next, we focus on the efficiency and effectiveness of inference scaling techniques on the MM-Vet benchmark. We compare the newly introduced stage-level beam search from LlamaV-o1 with our beam search method. Both are assessed based on MM-Vet scores and inference time, using a single NVIDIA A100 GPU. For the stage-level beam search, we find that increasing the number of beams leads to incremental improvements in the MM-Vet score, rising from 60.3% with 1 beam to 62.9% with 4 beams. However, this comes with a steep increase in computational cost, as the inference time jumps from 3.8 GPU hours for 1 beam to 54.1 GPU hours for 4 beams, making it less practical for real-world use. In contrast, our beam search method achieves better MM-Vet scores while keeping inference time constant, with a time complexity that remains efficient. With just 1 beam, our model outperforms LlamaV-o1, scoring 63.63% compared to 60.3%. As we increase the number of beams, our score improves to 65.40% with 4 beams, requiring only 4.2 GPU hours, a fraction of the cost of Java. This shows that our beam search is not only more efficient but also more accurate and suitable for real-world applications.